we said that entropy is a measure of the randomness or disorder of a system. Okay. In thermodynamics, we say that the greater the disorder, the greater the entropy of the system. Now, for us to illustrate this idea or this thermodynamic quantity, we can consider a deck of cards. Okay, when you have a new deck of cards, and when you look at how the cards have been arranged, they're usually arranged in a very orderly manner. Okay, maybe you have hearts, and then clubs, and then diamonds, and so on and so forth. Okay, arranged in that order for each set of cards. Now, when you start shuffling these cards, what you are having is like you are now introducing disorder into the deck of cards. The possibility of you arriving at the initial order that was there is highly improbable. Okay? But the possibility of you achieving a particular disorderly state is very high because there are various possibilities that you can get as you're shuffling the cards. Okay, so we say that an ordered state in our previous example where we were considering the freshly opened deck of cards, that orderly state has a low probability of occurring, and hence it has small entropy. Okay, while when you consider a disordered state, as you're shuffling the cards, a disordered state has a high probability of occurring, and therefore we say that it has a large entropy. When you're considering about the possibilities of arrangement in a particular system, we have to consider what we call the microstates. Microstates is the ways of arrangement of the particles within the system. So in this system, we are considering a case where we have 4 colored balls. Okay. And there are various ways of arrangements. So for example, the first distribution here, the distribution is described as arranging the 4 balls in the gray compartment. There is only one way of arrangement of those balls in that gray compartment. So for this particular distribution, we can say that there's only one way of arrangement, or there is one microstate. Okay. Excuse me. So there is one microstate for this type of distribution. The second distribution, the instruction for this distribution is how many ways can you arrange 3 colored balls in the gray compartment and 1 in the second white compartment. So there are various ways you have to interchange the colored balls, okay, such that each ball is arranged in the white compartment, the second white compartment. So if that happens, then you have 4 ways of arranging the balls. Okay. So since there are 4 ways, we say that there are 4 microstates for this particular second distribution. Okay. The third distribution, it says the instruction there is how many ways can you arrange 2 balls? Can you arrange the 4 balls such that 2 are in the gray compartment, gray first compartment, and 2 are in the second white compartment. Okay, so of course you have to interchange the balls such that you only have 2 in each compartment. Okay, now when you do that, you find that there are 6 ways of arranging these 4 balls. So for this star distribution, where you have 6 ways of arranging these balls, then we say that there are 6 microstates. Okay. Now, the probability of occurrence of a particular distribution, it depends on the microstates, the number of microstates in which the distribution can be achieved. The first distribution here, where you have only one way of arrangement, this one has a low probability because there's only one way. Okay. As the number of microstates increases, the probability of that distribution taking place increases as well. Okay, so the more the microstates, the higher the probability of a particular distribution being achieved. Okay, now Boltzmann, someone who studied entropy in the late 19th century, showed that entropy of a system is related to the natural log of the number of microstates. Okay, and he showed that the entropy of a system is directly proportional to the number of microstates. So the higher the number of microstates, the higher the entropy of a particular system. So entropy, which is S, is equal to K natural log of W. Okay, where W here represents the microstates, and this K is what is called the Boltzmann constant, and it's given as 1.38 times 10 to the power minus 23 joules per Kelvin. Okay. So since entropy is a state function, it means when a system moves from one state to another, you can be able to find the change in entropy. So change in entropy is given by final entropy minus the initial entropy. But then if you consider this expression for entropy, then we can say that change in entropy equals to K natural log of final microstates or microstates in the final state minus K times natural log of Wi, which is the number of microstates in the initial states. So then this particular expression can be written as equal to K natural log of Wf over Wi. And this expression gives us an expression for change in entropy. Now, when we consider changes in state, moving from one state to another, and the relating entropy to the disorder that results in the changes of state, it gives us some insight. For example, if you consider a solid, the particles within a solid are in a very orderly state and in fixed positions. Okay, so it's a very orderly state, and if you have a very orderly state, the entropy of that particular system is low, because entropy is related to disorder. But as you move from the solid state to the liquid state, the particles within the liquid are not in fixed states. They are moving about a bit. Although there's still some attraction between them, they still are able to move around. So that ability of being able to move around, it means that there is a number of ways that the particles can be arranged within the system. So therefore, that increase in microstates leads to an increase in disorder and thus an increase in entropy. When you move from a liquid to the vapor phase, there's even a more increase in the disorder. So when you're moving from a liquid to the vapor phase or the gaseous state, there's an increase in entropy. Okay. When you consider the process of forming a solution, okay, what is happening is that you are introducing more particles into the liquid, okay, by dissolving the solute in the solvent. You're introducing more particles in solution, and this creates a possibility of several ways of arrangement of the particles within the liquid. So this results in an increase in entropy. So more particles by dissolving solute in the solvent. This leads to increase in microstates, the number of ways that the particles are arranged in the system. Hence, this leads to an increase in entropy. The only instance where you are increasing the number of particles and it does not result in increase in entropy is the case of hydration. Okay, hydration is where you have an anhydrous salt. Okay, just a second. I don't know why this has appeared here. This ribbon down here, because it is stopping me from okay. Now, this process of hydration is where you have an anhydrous salt. Yeah, when you have an anhydrous salt plus water, you form a hydrated salt. Okay, so the anhydrous part with some water molecules. Okay, so although you introduced new particles into the system, but the salt that you generate in the hydration process is crystalline in nature. Okay, and you know crystals tend to be quite orderly in nature. An example of this would be if you have sodium anhydrous sodium sulfate, I think that is the N2SO4, and then plus water to give us the hydrated salt, which would be hydrated sodium sulfate. Okay, so let's say this is XH2O. So although you have increased the number of particles, but since you are forming crystals which are very orderly, the hydration process does not lead to increase in entropy. Okay, so that is the only exception. But the process of making a solution leads to increase in entropy because you are increasing the particles within the system. Okay. Now, in the case where you have a solid, a system being a solid, and then you are heating that solid to a higher temperature, what happens? This process also leads to an increase in entropy. Although you're not changing the state of the solid, but there is something happening to the particles within the solid. Okay. For example, there might be some rotation taking place in the solid, okay, or some vibration like this one. And these vibrations means there are various ways that the particles are being arranged within the solid system. So this increase in ways that the particles are arranged, it means that you have more microstates. And the more the microstates, the higher the entropy. So heating increases the entropy of a system. This increase in energy is distributed or dispersed among quantized energy levels. So the particles within the solid are going to have to exist at different energy levels. Therefore, we say that there are more microstates, or there are more microstates available for the particles at a higher temperature. So the entropy of the system also increases with the increase in temperature. We can also talk about standard entropy. So this is the entropy of a particular system, and it's referred to as absolute entropy, and it is measured usually at a pressure of 1 atmosphere and at 25 degrees Celsius. So we will see how this in a few slides down the line. We are going to see how this particular absolute entropy is determined for a particular substance. It's usually obtained by calorimetric methods, and this is an absolute value, not a change in entropy, but an absolute value for entropy. So here we have an example of some substances and their standard entropies, okay, which are in joules per Kelvin per mole. So for example, when you consider water in the liquid phase and in the gaseous phase, you can see clearly there is an increase in entropy when you move from the liquid phase to the gaseous phase. And the same is observed for bromine from the liquid phase and the gaseous phase. You can clearly see the differences, okay? And then iodine, from the solid phase to the gaseous phase, you also see an increase in entropy. Now, for diamond and graphite, although they are all carbon compounds, they have different entropies, okay? So for diamond, it's 2.4 joules per Kelvin per mole, but for graphite, it is 5.69. And we know why that would be the case. Diamond, the carbon within diamond are in fixed positions, okay? It's pretty fixed. You have the tetrahedral structure for the arrangement of carbons within diamond, okay? Something like this. And each carbon is attached to another carbon. There is no free carbon within diamond. But in the case of graphite, you have a structure like this. Okay. So where you have a carbon being attached to two more, okay, and then you would have some free electrons, okay. So this leads to the structure of graphite being in layers. So you have layers which can slide on top of each other. So the fact that these layers can slide on top of each other, it means there are various ways of arrangement of those layers. So that increases the entropy of graphite. When you consider methane and ethane, both are gaseous substances. But then when you look at the entropies are different. Okay. The one for ethane is higher. And the reason for that is that methane has a possibility of you can have, since you have two carbons, there is a way that this bond between the carbons can be rotated. Okay? And this possibility of rotation means that there are various ways of arrangement of these molecules of ethane, okay, as compared to that of methane, which has only one carbon. So this possibility of rotation for ethane increases the microstates for the ethane molecule. I'd really request you guys to mute yourselves, huh? Because we are recording this lecture. So if you make any noise, you're messing up the whole recording. So this rotation of the ethane molecule, as opposed compared to the methane molecule, means that there are more ways of arrangement for the ethane molecule. That is more microstates, which translates to higher entropy, which is measured here in the standard entropy. For helium and neon, these are monoatomic gases. But when you look at the entropies, the one for neon is higher, slightly higher compared to that of helium. Despite the fact that the two are monoatomic gases. Now, the reason for that difference is that neon is slightly heavier than helium. And heavier monoatomic substances usually have very close energy levels. Okay. So the fact that you have very close energy levels, it means it's very easy for the particles to move from one energy level to another. So that means the particles within a sample of neon are going to be distributed in a number of energy levels, or they have the possibility of jumping from one energy level to another easily. Okay. And this increases the number of microstates for these atoms. Therefore, this increases the entropy as a result. So that explains the slightly higher entropy for neon as compared to that of helium. Okay. So having understood what entropy is, we want to now to use that idea of entropy for us to determine spontaneity of a reaction. And this brings us to the second law of thermodynamics. Okay. The second law of thermodynamics simply states that the entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. Now, when you talk about the universe in thermodynamics, We are simply talking about the system plus the surroundings. So the universe in thermodynamics is made up of the system under study, under focus, and its surroundings. Okay. So for a spontaneous process, we say that the change in entropy of the universe is always greater than zero. Essentially, what we are saying is that for a spontaneous process, the change in entropy is going to be positive. Okay? And then for an equilibrium process, the change in entropy of the universe equals to zero. Now, change in entropy of the universe is given by change in entropy of the system plus change in entropy of the surroundings. Okay. So this essentially, the two are the mathematical expressions for the second law of thermodynamics, that the entropy of the universe increases in a spontaneous process. So when it increases, okay, when it increases, it means that the change in entropy equals to a positive value, okay, for a spontaneous process. And it remains unchanged, okay? So when you say that it remains unchanged, it's that delta S is given by the final entropy minus the initial entropy. But if these two are the same, okay, the final entropy equals to the initial entropy, then change in entropy is going to be equals to zero. And that explains the mathematical expression. So, what we have said, for a spontaneous process, the second law says that change in entropy of the universe, that is delta S universe, must be greater than zero. But it does not place any restriction to change in entropy of the system and change in entropy of the surroundings. So it means it does not say whether the change in entropy of the system has to be positive or has to be negative, and the same for change in entropy for the surroundings. So that means the magnitude and the sign of these two are not specified, okay? So long as the sum of the two is going to give us a positive value, okay? But in the second case, for an equilibrium process, for this expression to be equal to zero, it means that the change in entropy of the system has to be equal to the change in entropy of the surroundings, has to be equal in magnitude, but different in sign. Okay, so when one of them is positive, then the other one has to be negative, and vice versa. Okay, so this one, if this one is negative, the other one has to be positive, so that they cancel out and give us a value of zero for the change in entropy of the universe. Okay, so this is what the second statement is saying here. For an equilibrium process, delta S universe is zero. In this case, the change in entropy of the system and that of the surroundings must be equal in magnitude but opposite in sign, so that they can cancel out to give us zero. Okay. In the case where you find delta S universe to be negative. So for example, you have a process A plus B, okay, giving us C plus D. If you have the delta S universe for this process being equals to a negative value, it means that the process is not spontaneous in the direction that has been specified. Okay, it is not spontaneous in the direction specified, but it would be spontaneous in the opposite direction. So in this case, C plus D giving us A plus B is going to be the spontaneous process in this case. So for us to be able to determine whether a reaction is spontaneous or not, we need to find the delta S universe, okay? Find out if it is positive or negative or equals to 0. And for us to do that, we will need to find the change in entropy for the system and also change in entropy for the surroundings. Okay. So that brings us to how to determine this change in entropy for the system and the change in entropy for the surroundings. Now, for the system, when you're considering a system, there's a reaction that is taking place in this system. So that particular reaction is now what we focus on. We want to find the change in entropy for that particular reaction. So if you have this reaction, A plus B giving us C plus D, also with the coefficients that have been indicated, for you to find the change in standard entropy for the reaction is going to be given by total entropy for the products minus the total entropy for the reactants. Okay, so that the difference between the two is what gives you the change in entropy for the reaction. Because as you're moving from the reactants to the products, you're moving from one state to another. So the final state here is the products, and the initial state is the reactants. So in general, we can write this. Please take note of the coefficients. So the entropy for C is going to be given by the standard entropy for C times its coefficient in the reaction. And the entropy for D is going to be given by standard entropy for D times its coefficient in the reaction. And the same can also be said for A and for B. Okay. So in general, this expression here gives us the change in entropy for a given reaction. It is the sum of the standard entropies for the products minus the sum of the standard entropies for the reactants. M and N represents the stoichiometric coefficients in the reaction. So this, just as we have seen here for A, B, C, and D. So using this expression for determining the change in entropy for a reaction, we can consider these three reactions here. Okay, we have been given the standard entropies down here. Okay, and the units are in joules per Kelvin mole. So we're supposed to calculate the changes in standard entropies for the three reactions which are taking place at 25 degrees Celsius using this expression that we have here. So I want you to take the time, take about 5 minutes, and determine the standard entropies for these three reactions. Okay, so take 5 minutes, and then we will come back and look at the standard entropy changes and also make some observations for the three reactions. Okay, so take 5 minutes. Okay, so do you have any quick answers for the standard entropy changes for the three reactions? Feel free to unmute yourself and give an answer. Any quick answers?
Yes, I'm getting 160.5 for the first one.
For the first one, you're getting 160.5. Okay, that is joules per Kelvin per mole. Huh?
Yes.
Anyone with the second one?
Negative 199.
Negative 199 joules per Kelvin mole. Okay. What about the third one?
Positive 20.
You have positive 20 joules per Kelvin mole. Okay. So looking at the three reactions, there are certain observations that we can start making, and these observations can help us to predict, like even before you calculate the change in entropy for a particular reaction, you can predict what value you're going to get. So when you consider the first case, first reaction, you're moving from a solid reactant to you have a solid and a gaseous product. So that means you're moving from a solid phase to gaseous products. Okay. And when that is the case, remember we said moving from solid to gaseous, there's an increase in entropy. So the change in entropy is likely, in such a case, it's likely to be a positive value. So that's an observation that we can make. If a reaction produces more gas molecules than it consumes, then the change in standard entropy is going to be positive. Okay? So in this case, the reactants are solids and it is producing more gaseous products. So change in entropy is positive. In the second case, we have gaseous reactants and a gaseous product. Okay? So this one is tricky. You have to look at the number of moles. How many moles of reactants do you have? You have 4 moles of reactants. How many moles of gaseous products are you getting? 2 moles. Okay? So there's a reduction in number of moles. So where you have a reduction in the number of moles of the gaseous species, there's a reduction in entropy. So the change in the standard entropy, since the final entropy is lower than the initial, then you're going to have a negative entropy. Okay. So we say the total number, if the total number of gas molecules diminishes, which is the case for the second reaction, the change in entropy is, in standard entropy, is negative. Okay. When we look at the third reaction, here we have gaseous reactants giving gaseous products. Okay. Now, when you look at the number of moles, you have 2 moles of reactants and 2 moles of the product. So it's like the number of moles does not change. It remains constant. So the change in entropy that you get can be positive or it can be negative. But one characteristic of such reactions is that the value is going to be low. The change in entropy, the value, whether it is positive or negative, the value of the change is going to be small. So in this case, we got 20 joules per Kelvin mole. Okay, so that is the last statement here. If there is no net change in the total number of gas molecules, then change in entropy, standard entropy may be positive or negative, but will be relatively small numerically. In this case, we had 20 joules per Kelvin mole. So relatively, when you compare with the other two reactions that we have looked at, it is relatively small numerically. So those are some of the observations that you can make about the change in standard entropy of a particular reaction. So this example is simply how you would determine the change in entropy for a particular reaction. This takes us, the observations that we have made here, they make sense because gases have greater entropy than liquids and solids. So when you're moving from gaseous, from solid or liquid reactants to gaseous products, there's an increase in entropy. Because if you're ending up with gaseous products, the final entropy is going to be higher compared to the initial entropy. So the change in entropy is going to be positive. And vice versa. If you are consuming the gaseous species in a particular system, that is the reaction, then you're going to have a negative change in entropy because you're consuming gaseous species. You are reducing the gaseous species in the system. So this results in lower entropy that you end up with finally. So this shows that you have a negative change in entropy. Okay, so we have seen how to determine the entropy of a system. In this case, our system is a reaction. How then do we determine the entropy changes of the surroundings? Okay, so the entropy of the surroundings depends on the type of reaction that is taking place in the system. So the reaction taking place in the system can either be exothermic or endothermic. So this first example here, you have a case where you have an exothermic reaction that is taking place in the system. So that means the system is releasing heat into the surroundings. Okay. Now, when you release heat into the surroundings, the particles within the surroundings are going to be absorbing heat. They become more energetic, so their movements become more random. So the disorder increases as a result of the heat from the system. So when the disorder increases, then there's an increase in entropy for the surroundings. Okay. When the reaction in the system is endothermic, meaning that it absorbs heat from the surroundings, or it is being heated by the surroundings, okay, it means that the particles within the surroundings are losing heat, okay? And when they lose heat, then they become less energetic in their movements. So therefore, the disorder is kind of reduced in the surroundings. And that decrease in disorder leads to a decrease in entropy. So we see that the entropy or the change in entropy of the surroundings is related to the enthalpy change in the system. So we say that change in entropy for the surroundings is directly proportional to negative change in enthalpy in the system. Okay. And this particular negative here takes care of whether you have an exothermic reaction or you have an endothermic reaction. If you have an exothermic reaction in the system, change in entropy, in enthalpy, is going to be negative. So a negative value for this, okay, negative value for change in enthalpy in the system times this negative here means you have a positive value, or you have a positive change in entropy for the surroundings, meaning there's an increase in entropy for the surroundings. Okay. If the reaction that is taking place in the system is endothermic, so this delta H system or change in enthalpy in the system is positive. Positive times this negative is going to be a negative value. So that means the change in entropy for the surroundings is going to have a negative value. That is, there's an increase, there's a decrease in entropy. Okay. So this negative essentially takes care of that, whether you have an exothermic reaction or you have an endothermic reaction. Okay. Now, another thing that the change in entropy for the surroundings depends on, so it first of all, it depends on the enthalpy change in the system. It also depends on the temperature of the surroundings. Okay. So it also depends on the temperature of the surroundings. If the temperature of the surroundings is not, let's say, it's very high, for example, let me just change this. So if the temperature of the surroundings is very high, let's say you have a very high temperature, what that means is that the particles within the surroundings are already very energetic. Okay. So if the reaction in the system is exothermic, that is, it's releasing some heat into the surroundings whose temperature is very high already, there is going to be some slight change in the disorder within the surroundings. The particles are going to absorb the heat, but the change in entropy is not going to be so large. It's going to be small because the particles are already energetic. So the change in entropy is not going to be that much. It's going to be, yes, it's going to change to increase a bit, but to a very small extent. But if the temperature of the surroundings is low, okay, if the temperature of the surroundings is low, it means the particles within the surroundings are moving around, but not so energetic. So if you have the system releasing heat into the surroundings from the exothermic reaction, the particles that are within the surroundings are going to gain a lot of energy. Okay. So their movements are going to be more energetic. The increase in entropy for this case is going to be quite large. Okay. So you see there's a certain relationship between the temperature of the surroundings and the change in entropy that results. If the temperature is high, the change in entropy is not so high, small. If the temperature is low, the change in entropy is quite high. So there's an inverse, it means there's an inverse relationship between change in entropy and the temperature of the surroundings. So we can combine these two expressions. Okay, this is the change in entropy for the surroundings. We can combine these two expressions and come up with an expression for change in entropy for the surroundings. So the expression that we come up with is change in entropy for the surroundings equals to negative change in enthalpy of the system, okay, divided by the absolute temperature of the surroundings, okay. And this is the expression now that we use to determine the change in entropy for the surroundings. Okay. All this we have said. So we have this expression that we have ended up with here. So using this expression, we can try and find, so suppose you have this reaction here. This is the production of ammonia. This is the change in enthalpy for this particular reaction. And you're supposed to calculate delta S system for this particular reaction and delta S surroundings, and then determine whether this reaction is spontaneous or at 25 degrees Celsius. Okay. Now for delta S system, this one we have already determined in the three examples, the three reactions that we looked at to determine the change in entropy for the system. And we found that this one, for the production of ammonia, we found it to be negative 199 joules per Kelvin mole. Okay, we have that. So for us, what we need to do is to determine delta S surroundings. Okay, delta S surroundings, we can find it using this expression, that is negative change in enthalpy for the system divided by the absolute temperature. So this one equals to negative into negative 92.6. So remember, this one is kilojoules here. So we can multiply this by 10 to power 3. Okay, joules per Kelvin, no, joules per mole is enthalpy change. Then divide by the absolute temperature, 25 degrees Celsius. In absolute terms, you add 273. So this becomes divided by 298 Kelvin. Okay. So what do you get for this? Any quick answers?
One 1.07.
1.07. Anyway, do we confirm that?
310.73.
So about 311, eh?
Yes.
Joules per Kelvin mole. Okay. So remember, for us to determine whether the reaction is spontaneous, we need to find delta S universe, okay, which is the sum of delta S system plus delta S surroundings. Okay. So we have the two. For the system, we had found this to be just a second. We had found this to be negative 199 joules per Kelvin mole. Okay. Then plus what we have found here is 311 joules per Kelvin mole. Maybe we can do this and then put the units outside. Okay, so when you add the two, you get the delta S universe to be equal to 112 joules per Kelvin mole. So we see that delta S universe in this case is a positive value. Okay. And when you have a positive value, we say of the delta S universe, change in the entropy of the universe, then we say that the reaction is spontaneous. Okay. So this particular reaction is spontaneous at 25 degrees Celsius. But the fact that it is spontaneous, just because the reaction is spontaneous, does not mean that it will occur at an observable rate. So for example, that reaction of synthesis of ammonia at room temperature, that is at 25 degrees Celsius, is actually extremely slow. And if you look at the Haber process, just you can Google that, you find that it usually takes place at very high temperatures and high pressures for it now to take place at an economical rate, which is fast enough. Okay. So thermodynamics in this case has enabled us to determine whether the reaction is spontaneous under the specified conditions. But it does not tell us how fast the reaction will occur. So it has only told us that this particular reaction here of synthesis of ammonia at 25 degrees Celsius is spontaneous because we are getting a positive delta S universe. Okay. But it does not tell us how fast it is. That one you have to observe. And that is the focus of chemical kinetics, which is what you did in SCH 3204. Okay, so here thermodynamics has enabled us to determine whether the reaction is spontaneous or not. Okay. So we know what entropy is. That is the disorder within a system, the measure of disorder within a system. And we know how we can use the change in entropy for the system and the surroundings for us to determine the spontaneity of a reaction, okay, by using the concept of entropy. Now, we shift to the third law of thermodynamics and see how it is applied to determine the absolute entropy of systems. Okay, so first of all, for the third law, we are considering perfectly crystalline substances at 0 Kelvin or at absolute 0. Okay. Now, when you consider perfectly crystalline substances, if you consider a perfectly crystalline substance like this, just an example here. Okay. The particles within this substance are in fixed positions. Especially, we know that at higher temperatures, there would be some vibrations. Okay. But at 0 Kelvin, the molecular motions are at a minimum. Okay. They're at their lowest. The vibrations are almost non-existent. So what that means is that these particular particles within this crystalline substance are in fixed positions, and they do not have many ways of arrangement because of the lack of vibrational motions or molecular motions. The particles are in very fixed states, and there's only one way of arranging these particles within the crystal. So we say that the number of microstates for these particles or for this system is 1. There's only one way of arrangement of the particles within the system. So if the number of microstates is 1, then entropy, that is S, which is given by K natural log of W. If W is 1, then K natural log of 1 equals to 0. And this gives us the expression for the third law of thermodynamics, which simply states the entropy of a perfect crystalline substance is 0 at the absolute 0 of temperature. The entropy of a perfect crystalline substance is 0 at the absolute 0 of temperature. Maybe I can add something here of a pure perfect crystalline substance is 0 at the entropy at the absolute 0 of temperature. So the reason why I have added that that word pure there is because if you incorporate impurities within a crystalline substance, it means that now you are introducing more possibilities of arrangement of the particles within the crystal. Okay, and introducing these more possibilities, it means now the number of ways of arrangement of the particles is not 0, is not 1 anymore. You're going to have more ways of arrangement of the particles. So therefore, if you have impurities, then the entropy is not going to be equal to 0. Okay. Now, this particular third law of thermodynamics actually enables us to determine absolute entropy. So for example, if you look at this particular plot here, this is a plot of entropy against temperature. So here it is at absolute zero, where the substance is at absolute, in the crystalline state. And here the entropy is also zero, according to the third law of thermodynamics. Now, if you raise the temperature maybe to somewhere around here, so this is the initial state and this is the final state. You have raised the temperature in that direction, okay, from 0 Kelvin to somewhere around here. Now, if you want to find the change in entropy, there it's going to be given by the final entropy minus the initial. But according to the third law of thermodynamics, this initial entropy at 0 Kelvin equals to 0. So actually the change in entropy that you're going to measure is actually the absolute entropy at that particular temperature here. So if this particular temperature is room temperature, for example, at 25 degrees Celsius, yeah, then the change in entropy that you are measuring here is actually the absolute entropy at 25 degrees Celsius. Okay, so the third law of thermodynamics essentially enables us to determine the absolute temperature, the absolute entropy of a particular substance. Now, this considering this diagram here, this plot of change in entropy, and not change in entropy, but absolute entropy against temperature, it actually gives us some interesting insights about what happens to the substance as you cool it. So, for example, if we are starting with a gaseous substance, the entropy is usually very high. Somewhere, if you're starting from somewhere around here, the entropy is quite high. Okay. Now, as you cool the substance, so as you're moving towards the left of this diagram, you are cooling the substance. Okay, but you're moving towards lower temperatures. So as you're cooling the substance, there is a change in entropy along this curve. Okay, so it changes until it reaches a certain point where now this is the boiling point of the substance. Oh, now at this point it starts condensing into liquid. Okay, so at this point the temperature remains constant for some time until all the substance has been condensed. Can you please mute your mics? Okay, so it remains constant here until the whole substance has been condensed. So there's a sharp decrease in entropy here as the substance moves from the gaseous phase to the liquid phase. Okay, and then if you continue cooling the liquid further, the entropy of the liquid decreases along this curve until you reach the freezing point of the substance, and then there's a sharp decrease in entropy as the substance is as all of it is being frozen, becoming crystalline. Okay, once it is crystalline, and you continue cooling the substance further, the entropy also continues reducing along this particular curve. So it reduces until it reaches 0 Kelvin, where now, according to the third law of thermodynamics, if it is a pure substance, then the entropy at absolute 0 is going to be equal to 0. Okay. So this is an interesting plot, which kind of mimics the plot of when you're cooling a substance. Okay, when you say you plot a temperature of a particular substance as you're cooling it, you also have a similar change. I think temperature and pressure diagram. You also get a similar plot where at a particular point, the freezing point or the melting point, you have the temperature remaining constant for a while before it continues dropping further. Okay. So the entropy of any substance at a temperature above 0 Kelvin is greater than 0. Just from this diagram here, at any temperature above 0 Kelvin, from this plot, the entropy of any substance is going to be non-zero. It's going to be higher than 0. Okay. If the crystal is impure, this one we have stated, or if it has defects. So if the crystal is not perfect, or if it has some impurities, then the defects and the impurities introduce more ways of arrangement of the particles. So then the entropy is going to be greater than 0, even at 0 Kelvin. Okay, because it will not be perfectly ordered, and the number of microstates would be greater than 1. Okay, so the third law of thermodynamics enables us to determine the absolute entropies of substances. So starting with the knowledge that the entropy of pure crystalline substances is 0, at absolute 0, we can measure the increase in entropy of the substance when it is heated from 0 Kelvin to 298 Kelvin. So from 0 Kelvin, from absolute 0 to room temperature, you can measure the increase in entropy. Okay. And we had said this, we said the initial, according to the third law of thermodynamics, this initial entropy is 0. So therefore, measuring the change in entropy is essentially measuring the absolute entropy. So because the entropies are usually determined at 1 atmosphere, therefore the absolute entropies are referred to as standard entropies. Okay. The numerical definition of entropy was introduced by Clausius again. And according to him, entropy of a system that is not undergoing any chemical change, of any chemical or physical change, is a constant quantity when there is no flow of heat. Okay. So he said that for a substance that is static, there is no change that is taking place. Okay. And there is no heat flowing into the system or out of the system, then entropy of that system is a constant quantity. Okay. If there is any flow of heat, the entropy is going to change. If there is heat flowing into the system, the entropy is going to increase by Q over T. So it's going to increase by this magnitude. if there is heat flowing into the system. But if heat is flowing out of the system, okay, if heat is flowing out of the system, the entropy is going to decrease by the same measure, minus Q over T. So it's going to decrease by minus Q over T. For a reversible change taking place at a fixed temperature, the change in entropy delta S is equal to the heat absorbed or the heat evolved, okay, that is Q, divided by the temperature T. Okay, so delta S equals to Q over T. Change in entropy for the system equals to Q over T. And this one mirrors what we found when you're determining the delta S for the surroundings. Remember, we were considering change in enthalpy divided by temperature. But here we are considering the change in entropy for a particular system. So it decreases or increases by Q over T. And the change in entropy is given by Q over T, where Q is the heat absorbed or evolved by the system. Now, when you look at this particular expression, heat is usually measured in terms of joules per Kelvin. Okay, so if you're talking about 1 mole of a substance, then it's going to be joules per Kelvin per mole, or joules per mole per Kelvin, or the heat can also be measured in calories. Okay, so heat can be either in joules per mole per Kelvin or calories per mole per Kelvin. Okay, and the temperature, absolute temperature, is in kelvins. Okay, so the units of entropy, we talk about entropy units, which are usually calories per mole per Kelvin. Okay, all deriving from this expression here. Or when you talk about the SI units of entropy, it is in joules per mole per Kelvin, all also deriving from that expression that we looked at in this previous slide here. Okay. Okay. I want us to shift gear and kind of revisit something that we have looked at. Remember, in our introduction, we looked at processes. And one of the processes that we defined was a cyclic process. So I want us to take 2 minutes and then we come back and revisit these cyclic processes and see how we can apply this now where you have heat exchanges. What happens? Yeah. Okay, now when we introduced cyclic processes in our introductory class, we said if you are starting from an initial state here, okay, where you have the system having an internal energy of U1, for example, okay, and then you move the process through a series of changes, the system through a series of changes, okay, and then finally end up at the initial state. If you consider the change in internal energy, it is going to be equal to U1 minus U1. So essentially here you have change in internal energy being equal to 0. So if this delta U equals to 0, remember from the first law of thermodynamics, we say delta U equals to Q plus W, where Q is the heat and W is the work done by the system. So if this particular delta U equals to 0, then it means you can come up with an expression Q equals to negative W. So the work done by the system during all these changes, as the system is moving through a series of changes in the cyclic process, is equal to the heat absorbed by the system. So the work done for a cyclic process, yeah, the work done by the system is equal to the heat absorbed by the system. Okay. So we have what we call heat engines. Heat engines are examples of machines that undergo cyclic processes. Okay. So they undergo a series of changes. They absorb some heat and do work. And here we have said that the work done by the system, in this case a heat engine, is going to be equal to the heat absorbed by the system. So heat engines take advantage of the fact that if you have a hot body, okay, so let's say we have a hot body here, which is connected to a cold body, there's a spontaneous reaction that takes place. Heat is going to flow from the hot body to the cold body. So it's a spontaneous process. So what the heat engine does is that it intercepts this heat, converts some of it to work, okay? And then the rest is released to the cold body. So a machine which can do work by using heat that flows out spontaneously from a high temperature source to a low temperature source sink is called a heat engine. So in this case, this hot body is referred to as a heat reservoir. Okay, it's referred to as a heat reservoir. And then this cold body here is referred to as a heat sink. Okay. So this particular machine here in the middle that can do work by using that heat is called a heat engine. Okay. The heat engine takes heat energy from a high temperature reservoir, okay, and converts some of it into work, and then returns the unconverted heat a low temperature sink, that is the heat sink. Okay. So this is essentially what I had sketched in this slide. So here you have we have a heat reservoir which is at a higher temperature TH, okay, and the heat sink is at a lower temperature TC. So the heat engine absorbs heat from the heat reservoir, does work, and then the rest of the heat that is not converted to work is passed to the heat sink. And this is a simple diagram that represents how a heat engine works. Okay. So how the principle of a heat engine, how it operates. For example, a steam engine, you're going to see its operation in a couple of slides. It's a typical heat engine. It takes heat from a boiler. Okay, the boiler is where now the steam is generated. Okay, water is heated up and it generates steam. So it takes heat from the boiler, which is a high temperature source, converts some heat to work. Okay, so it converts some of the heat from the steam to work and returns the unused heat to the surroundings. Surroundings here act as the low temperature sink. Okay, so the boiler is the high temperature source and the surroundings are the low temperature sink. So a heat engine running on a periodic cyclic process can yield work continuously. So steam engines have been used to run turbines which generate electricity. Okay, so the work here for this engine is running the turbine, and the turbine generates electricity. Or the steam engine has also been applied in running the pioneering trains. They are usually running with run by steam engines. Okay, so you would use coal to generate steam, and then the steam is going to run the engine for the train, and the train can be able to move forward. So the principle of how this works is usually simple, and this we can look at a hypothetical heat engine. In this case, we consider a cylinder, okay, a cylinder that contains an ideal gas, and then it is enclosed by a piston. Okay, then this particular gas that is enclosed here can undergo expansion, especially when the system, if you consider this as a system, when it is heated, okay, the gas expands. Okay, and then when it is cooled, so when it is heated, the gas expands. So this particular piston moves in that direction. When it is cooled, okay, the gas contracts. So we have the piston moving in that direction. So if this particular gas is being heated and cooled continuously, the piston is moving in that direction. So there's a cyclic process. It moves up and down, up and down, up and down. And that particular movement can be made to do some work. Okay, so it can be made to do some work. And this is essentially the principle behind the operation of heat engines. We can look at an example of a steam engine and see how that principle of a heat engine is applied in doing work. In this case, the running of a locomotive using steam.
How do steam locomotives work? With the invention of the commercial steam engine starting the Industrial Revolution, These icons of progress made travel and transportation by rail a viable option, cutting travel times and connecting communities. Here's a somewhat simplified steam locomotive. With many trains of this era, the boiler is clearly distinguishable. A steam locomotive needs water and fuel, usually coal, carrying them either on the locomotive itself or in a tender pulled behind. The fuel is used to run a fire inside the engine, burning inside what's called the firebox. The fire is managed by the fireman in the cab, who, along with the driver, is needed to run the steam locomotive. The firebox sucks air from underneath the train to keep the fire from starving. The solid fuel sits on top of grates, through which dead ash can fall down into the ash pan. The firebox allows heat and smoke to escape the chamber through the so-called fire tubes, running the length of the boiler. The boiler wraps around the firebox and fire tubes, thus heating the water inside to boiling point, creating steam. As more and more water evaporates, steam builds up inside the boiler, creating pressure. Inside the steam dome, the steam can find a way out of the boiler towards the cylinders. In case the pressure becomes too high and the boiler risks exploding, a safety valve pops to relieve pressure. The amount of steam exiting the boiler is controlled using the regulator valve. This is effectively the throttle of the steam locomotive. Because as the steam runs down to the cylinders, we get to the part that actually drives the wheels. There are two sets of cylinders, one set on each side of the train. Steam engines on steam locomotives are so-called reciprocating piston engines. Each set has one cylinder with a piston, connected to the driving rod, which in turn is connected to the driving wheel, which can be connected to the other wheels. The other cylinder contains the slide valve, which allows fresh steam to enter and used steam to exhaust from the piston cylinder. This way, the piston is pushed once from both sides to complete one rotation, creating that reciprocating motion, which is then used to rotate the drive wheel. The steam, now done with its job, exits towards the smoke box, where it joins any smoke coming off the firebox to escape out the chimney. Do you want, for instance, a more in-depth?
Okay, so that is a small illustration on how a heat engine can derive heat from the heat reservoir, do some work, in this case running the steam, running the locomotive, and then the rest of the heat that is not used to do work is now released to the surroundings, which is the heat sink in this case. The efficiency of a heat engine usually calculated using this expression here. Efficiency equals to the useful work output divided by the energy input times 100%. Now, we are going to see that this particular expression can also be written as this. We're going to see how this one is arrived at in the next lecture. You can use the temperatures of the heat reservoir and the heat sink to determine the efficiency of the heat engine. So in this case, efficiency is given by the difference between those two temperatures, TH minus TC, divided by TH times 100%. Okay. Now, for you to improve the efficiency of the heat engine, you can play around with these two temperatures, the high temperature source and the temperature of the heat sink, to see to increase the difference between them. So here you can reduce TC as low as possible, okay, and decrease TC as low as possible, and increase pH as high as possible. Okay, because when you increase that difference, yeah, then you are increasing the efficiency. It is desirable that you get TH minus TC to be as close as possible to TH. Okay, so that can be done by making this almost zero. Okay, such that now when you come to this expression, you're essentially getting TH over TH being equals to 1. So then times 100%, you're moving as close as possible to 100% efficiency. Now that one is usually not possible because getting TC to be equal to 0 is impossible. Yeah. And also getting TH to be as high as possible is also to be infinite, for example, is also impossible. So getting an efficiency of 100% is not possible. We can look at an example here of a power plant where steam is being used to run turbines. So here you have superheated steam at 560 degrees Celsius being used to drive a turbine to generate electricity. And the temperature of the heat sink is 38 degrees Celsius. So using these temperatures of the heat source or the heat reservoir and the heat sink, we can be able to calculate the efficiency. So you use the high temperature source, the low temperature sink, divide by the high temperature times 100%. So in this case, for this power plant, you get an efficiency of 63%. Now, this is actually very high efficiency, which is not possible. And the reason why this is the case is because there will be some losses. Some of the energy is lost through friction, through heat loss, and some complications in the machine. And this reduces the efficiency further to around 40%. So in practice, an efficiency of 40% is usually very, very high. Okay. So therefore, for what this particular efficiency means is that for every ton of coal that is used in the power plant, only 0.4 tons of coal generates electricity. The rest of the coal that is being burnt is just being lost in warming the surroundings, okay, which is an unfortunate thing. The ideal would be having a high efficiency as possible, but 60% of the coal is usually just burnt and lost as heat to the environment. So the ratio of work obtained in a cyclic process, that is W to the heat taken. So here we're talking about W divided by Q, heat taken from the high temperature reservoir, that is Q. This is essentially referred to as the efficiency of a heat engine. Okay. No heat engine can convert all the heat from a high temperature reservoir into work. Okay. So that means you cannot get 100% efficiency. Now, the person who arrived at this particular conclusion that there's no heat engine that can convert all heat to work, yeah, is a scientist called Sadi Carnot. So he's the one who did some calculations and was able to show that heat engines actually have limitations. You cannot convert all the heat of a heat engine, or the heat engine cannot convert all the heat it absorbs to work. Some of it is lost. Okay. He's the one who came up with some some calculations. And these calculations, we are not going to look at them today, but we are going to look at them next week. So in case you want to read ahead, you can go and look at what we call the Carnot cycle. Okay. He looked at the Carnot cycle, where there's an engine, an ideal engine that is undergoing a cyclic process. And he was able to show that this particular engine does not convert all the heat that it absorbs to work.